We looked at general tree in last tutorial where we went over electronics product category example and we implemented a code in Python for general tree. In this tutorial we are going to talk about binary tree, especially binary search tree. This will be two-part tutorial. In this one, which is part 1, we'll go over search and insert operations. We'll go over some theory first and then we'll do coding in Python, and as usual we have an interesting exercise for you to solve. So make sure you watch till the end. In the part 2 we will cover the delete operation. Let's get started. First, we need to understand what kind of problem does a binary tree solve. Well, in many programming languages such as Python, there is this thing called set, and set is more like a list. The only difference is that when you insert elements in the set, it makes sure those elements stay unique. So for example, if you are iterating through this kind of country records, if you just store them in a list, then you can have duplicates like this. See, India is repeated 2 times, USA twice. But the same thing if you store in a set, the set will remove the duplicates. So this is an important data structure which is available in Python, Java, different programming languages, and you will find it very useful. Now internally, to implement set, one of the ways you can use is binary search tree. So binary tree is nothing but a regular tree with a constraint that it has at most 2 child nodes. Here this node 12 has 2 child nodes, 7 and 14. 20 has only one node, 23, but which is okay. The maximum number of child nodes that a particular node can have is 2. If you look at our example of a electronics product tree, here see cell phone had 3 nodes, so this is not a binary tree. Binary tree is this, at max 2 nodes. Now binary search tree is a special case of binary tree where the elements have some kind of order. Here the order is all the nodes on the left hand side of this particular node has value less than this particular node. So 15, if you look at this whole left tree, all the element values are less than 15. And on the right hand side, the values are greater than 15. And that applies to every node. If you look at any node, let's say this node 27, on the left hand side, you have values less than 27, which is 20 and 23. Right hand side, you have values greater than 27, which is 88. Another property is elements are not duplicated. So if you try to insert 27 again in this tree, it will not insert a duplicate. The elements are always unique. Now in this tree, if you want to search for number 14, what you can do is you can start with root node 15 and then you can see if the value that you're searching for is less than or greater than. 14 is less than 15, hence you are sure that it will be on a left subtree. So then you go here, you find 12. Now 14 is greater than 12, hence you know it has to be on a right hand side. This way what you're doing is in search operation, which is very common in computer application. Whenever you are writing software, searching through a list of elements is a very common operation, and you want to make sure you do that search in an efficient way. If I had stored all these numbers in a single list, then finding element or searching an element might be linear complexity, because if you search elements one by one, then your complexity will be order of n. But if you search this way, then what you're doing is every time you are reducing your search space by half. For example, here when you decided that 14 will be in a left hand side tree, you eliminated searching right tree. So you eliminated these 4 elements right on a first go. So thinking about search complexity, since we reduce our search space by half every time, let's say you have a number of nodes in a tree is 8. when you search for an element, when you make a decision whether the element is in a left tree or right tree, you're reducing the space by half. So now your space is 4. Then in that tree, when you further search, you make the search space by 2, 1. So if the total number of nodes in your tree is 8, you can search an element in 3 iterations, and 3 compared to 8 is nothing but a log to the base 2. Hence the search complexity in binary search tree is order of log n, which is very efficient operation. Like if you think about it, for 8 you achieved your search result in only 3 iteration. If you had done linear search, you might have to do 8 iterations. Now let's talk about inserting an element. Let's say you want to insert number 13 in this binary search tree. What you can do is first compare it with 15. You know that 13 is less than 15, hence you want to put it in a left subtree. So you will come here. Now you realize that 13 is greater than 12, so it will go in a right subtree. Then you come to 14 here, and then 13 is less than 14, so you insert it in a left subtree of 14. Here the insertion complexity is also order of log n. There are certain terms associated with binary tree in general, such as level, depth, number of elements, and there is this great video which will clear all your terms. So I highly recommend watching this video. I'm gonna provide a link of this video in the video description below. If you want to search through the binary search tree, there are 2 approaches you can take. One is breadth first search, and the second is depth first search. These are also called traversal techniques, which means how do you traverse your binary tree to find the element that you're looking for. In this coding tutorial, we are going to cover in order traversal, which is a depth first search traversal technique. So let's go over this depth first search traversal techniques a little bit. So let's say if you have a tree like this, in the in order traversal, what you do is you see, when you say in order or pre-order or post order, you are referring to your base node. So here the base node is 15. When you are doing in order traversal, you try to make sure this 15 node is in the order, which means you first visit your left subtree, then this particular node, and then right subtree. In pre-order traversal, actually you visit your root node first, then left subtree, and then right subtree. And in the post order, you visit your left subtree, then right subtree, and then your root node. So for example, in order traversal, okay, what you do is first you take left subtree. So when you are traversing this particular node 15, you come to your left subtree. Now how do you traverse left subtree? Well, you apply recursive technique here. So here again you apply the same rule. For 12, the left subtree is 7, so first you visit 7, then you visit 12, then you visit 14. So you get 7, 12, 14. Now your left subtree is done, so you visit root node, which is 15. So you see 15 here. Then you visit right subtree. Okay, right subtree is these 4 elements. Okay, there also you apply recursion, and you first visit left subtree of 27, which will be 20. And if you if you traverse that, you will get 20 and 23, then 27, and then 20, and then 88. In pre-order, you first visit the root node, which is 15, then left and right subtree. Remember, we always visit left subtree first and then right subtree. We never do right or right first and left after that in any of these techniques. So that's an easy way to remember. Left and right, they are always in sequence. Left comes first, right comes second. Now pre-order, post-order, in order is decided by where do you put your root node in between your left tree and right tree. If you put your root node in between left and right tree, it's called in order. If you put your root node before left and right subtree, it's called pre-order. So this is pretty easy to remember. Now let's get into coding. Here I have defined binary search tree node class. Remember, we are implementing a binary search tree. So there is a general tree where a node can have any number of elements. Binary tree will have at max 2 elements, and binary search tree is a binary tree with a specific order where left search tree has all the elements which are less than the current node, and the right hand side has all greater elements. So when you add a method called add child here, what I want to do is here I have this node. Okay, it could be a root node, it could be any node in the tree, and whenever I want to add a child with a value data, I need to check the value first. So what I need to check is if data is equal to self.data, which means the data that I am adding, that value already exists. See, if the value already exists, then you don't need to add anything because binary search tree cannot have duplicate elements. So here you just simply return. But let's say that is not the case, and the data that you are adding is less than the value of current node. What this means is here we will have to add this value, which means data, in left subtree. Okay, and if the value is greater than, then add data in right subtree. Correct? Okay, now let's write code to add it in a left subtree. So in a left subtree, first you need to check if your left element has some value, which means you are not a leaf node. Okay, if you are in else case, then it means that your left node is empty. Okay, and if left node is empty, then it's very simple. You can just say self.left is equal to binary search tree node of value data. So tree is a recursive data structure, hence you can just create a tree node, and that node will have a value is equal to data. So if you look at the constructor, data goes into self.data, and then left and right child would be none, and you created that node and assigned it to self.left. But let's say self.left already has some tree, some value, then what you will do is you will say self.left dot, think about it, what will you do here? Well, you will recursively call add child method with value data, because self.left itself is another small subtree which will have add child value. So you can call that method with data, and it will go into recursion. It will come here, and it will just work out. Similarly, you can add code for your right subtree. It will be very similar code. Okay, and once you have done this, now what we are going to do is, now I will implement in order traversal method, because using that method I can print all the elements in my tree. Okay, so I will define this method called in order traversal, and here this method will return a list of elements in your binary tree in a specific order. Okay, so let me just call elements as elements. So my goal here is to return these elements, and here I want to fill this list with all the elements in a binary search tree in a specific order. Now what is the specific order? In order traversal means first you're visiting your left subtree. So you need to check if self.left, meaning on the left hand side you have some elements, then you can say elements is equal to self.left in order traversal. it will require some thinking to understand this recursive method. When you say elements is equal to elements plus something, this method will return some list and it will add that list to this particular list. Now here it will call this function recursively, and when does a recursion end? Well, we need to write some more code here. So just assume that this method will work. Okay, so just leave this for a side. In order traversal means you visited your left tree, then you visit the base node, and then you visit the right tree. So let me write it down. So visit left tree first, then visit the base node, which means this particular node, and then visit right tree. Okay, so let's visit the base node. So the base node is nothing but in the elements you append self.data, which means this particular node has a value data and that I want to insert in elements. So I inserted elements from the left subtree, then this particular node, and now I will do same for right subtree. So if self.right, then elements is equal to elements plus self.right in order traversal. Here I have written my main method where I have this list of numbers and I want to build a tree out of this. Okay, so let me write a helper method called build tree, and this build tree takes elements as an input and this will build that tree for you. So your root node will be your binary search tree node, and let's say you assign the first element here as a root node, and then you run a for loop on elements which are in range 1 to the length of this elements. Okay, so we are going through this list and building the tree, and to build a tree we already added add child method here. So here you can just simply say add child, and then once the tree is built you return this root like this. Okay, so here I can now say numbers tree is equal to build tree with numbers, and once the tree is built I would like to print it, and the way you print it is by doing this traversal. See, if I do in order traversal, this particular method, if you look at this method, it returns all the elements in the tree in a specific order, in an ascending order. Okay, so let's run this code and see how this goes. Great, so you realize that when I give this list, it will build a tree, and then when you do in order traversal, it returns a list in a sorted order. So one of the utilities of binary search tree is to sort the elements in the list. The other utility is of course to implement set type of class where the elements are unique. So here if you give same element, let's say I give 18 and 4, it will remove those duplicates. See, 18 and 4 appeared only once. So to implement set, this can be very useful. Now I am going to implement a search method here in my binary search tree class where you are searching for some value. Now the first thing obviously that you do is if your self.data is equal to the value that you're searching for, then you are lucky, you can just return true here. But let's say if the value that you're searching for is less than self.data, what does this mean? Well, this means value might be, it's not guaranteed to be, but it might be in left subtree. Okay, and if value is greater than self.data, then it means val might be in right subtree. Okay, so if it is in left subtree, how do you implement it? First you check if self.left. In my left subtree, do I have any content? Okay, let's say that is your self.left is none. You know, you don't have anything, which means you have reached an end, and you can safely say return false, which means this value doesn't exist in my tree. But what if there is a left subtree? Well, in that case, you can again call a recursion. You can say self.left. Now in my left subtree, search for this value val. Okay, so I hope it makes sense. It will do a recursion. It will further go into left subtree and run the same function. See, this search is the same function that you're calling. And this concept in computer science is called recursion. And you'll do the same thing for your right subtree as well. Now let's test this method to see how this looks. So I did this traversal. Now I will do this. So numbers tree here, numbers tree dot search. Okay, let's search for value 20. And when I run it, it returns true because value 20 exists in this. Now how about 21? When I run it, it will return false because it doesn't exist. 200 also doesn't exist. So this makes your search operation very efficient. You achieve order of log and search complexity, which is pretty good. Here I'm showing you example of binary search tree which contains string. Okay, so it's not just for numbers. You can also use a string as an element. And here I have all these elements here, and I'm checking if UK is in the list and if Sweden is in the list. Okay, so here you clearly know UK is, where is UK? Yeah, UK is here. Sweden, there is no Sweden. Okay, so let's run this code and see what happens. So here say UK is in the list, none. Okay, so looks like we get none because here we need to return this. So this is what I was missing. We need to return this particular value. Okay, so that return was missing, and that is the reason we saw none. So let's run this again. And here it is saying UK is in the list, true. Sweden is in the list, false. If you want to print this particular tree in a sorted order, you can say country tree dot in order traversal, run it, and you just sorted your countries by alphabetical order. In Python, you can do less than, greater than type of operation with string as well, and that is the reason you are seeing this countries list in a sorted order. That's all I had for this tutorial. Now the most interesting part of this video tutorial, which is an exercise. I have this exercise for you. What you need to do here is the binary search tree node class that I implemented in this video tutorial. If you right click on this is available here. You can see that the whole class is available. You need to enhance this class and add following 5 methods. Find min, find max will find a minimum and maximum element. You already know how to traverse the tree, so you need to traverse the tree and just find a minimum element. You think about it, if you keep on going left, the leftmost node or leftmost leaf is actually a minimum element. Maximum is the rightmost leaf in your tree. Calculating sum means you just traverse through the tree and just take a sum of all of that. And we already implemented in this class in order traversal. So this method you can modify a little bit and you can get post order and pre-order traversal easily. So work on these exercises on your own first, and then you can verify your answer with my answer by clicking on this solution link. The link of this particular exercise is available in the video description below, so please go check it out. In the next tutorial, we will cover the delete operation in binary search tree and we'll have some more exercises. Thank you for watching.